Assalamu alaikum everyone. I am Najib bin Morshed along with my two groupmates Saklaina Imritvi and Tanvir Ahmed Shah. Today we will be discussing about one of the most concerning issues, which is air pollution in Bangladesh. Air pollution in Bangladesh isn't just an environmental issue, it's a public health emergency. Dhaka's PM 2.5 levels routinely hit 10 to 15 times the World Health Organization's safe limits, and the consequences are critical and reduce life expectancy. But what if we could predict dangerous air quality before it happens? That's where our research comes in. We have dropped machine learning models that use data to forecast air quality index categories like good, moderate, or unhealthy, giving policymakers and citizens a critical heads up. Traditional air quality monitoring relies on physical sensors which tells us what's happening now but can't predict what's coming. Our team set out to change that. We used a dataset from different locations in Bangladesh to criticalize PM 2.5, PM 10, nitrogen oxide, and carbon monoxide alongside with weather patterns. So this is not just about numbers on a screen. Accurate AQI predictions can save lives. Imagine hospitals getting advance notice of bad air days to stock up inhalers, or schools shifting recess indoors. For policymakers, our models pinpoint pollution hotspots, helping target interventions like traffic controls or industrial regulations. Our work proves that machine learning can be a powerful ally in Bangladesh's fight against air pollution. By turning data into actionable forecasts, we are not just predicting the future, we are helping to change it. We have reviewed 9 papers on quality and gained important knowledge. Recent research highlights machine learning's growing role in air quality prediction across highly polluted regions like Bangladesh and India. Studies demonstrate that random forest and XGBoost consistently outperform other models, with random forest achieving up to 97.2% accuracy in Dhaka and XGBoost excelling in hourly AQI prediction in India. Q pollutants driving AQI include PM 2.5, PM 10, nitrogen dioxide, and sulfuric acid, with winter months showing peak pollutions. Advanced techniques like integrate atmosphere physics with deep learning to predict pollutions in unmonitored areas. Challenges persist, such as data scarcity and real time monitoring gaps, but solutions like satellite data integration and ensemble methods show promise. In Bangladesh, policy interventions reduce some emissions, but vehicular exhaust, brake cleans, and transboundary pollution remains critical. These machine learning driven approaches enable timely public health warnings, targeted policy actions, and urban planning. Now I'm moving the floor to the next person. Thank you.
Thank you, Najib, for giving me the floor. So, to build this machine learning based air quality prediction system, which focuses on classifying air quality levels in Bangladesh using real world environmental data, we worked with a large dataset containing over 944,182 hourly records collected from 16 different locations, including Dhaka, Gazipur, and Chittagong. These records included 23 environmental attributes such as PM 2.5, PM 10, sulfur dioxide, nitrogen oxide, temperature, and wind speed. Our first and the most crucial step was data processing. Given the raw dataset's complexity and the significant number of missing values, almost 60% of our values were missing in the dataset, which was very challenging for us to handle precisely in order to get a preferable accuracy. But here we tried a different approach. We didn't remove all the rows containing null values, as this is a based time based sequential dataset. Removing these many values might affect the prediction of the model. However, many other rows had partial missing values. As shown in our analysis, some features like rain and V wind speed had over 600,000 null values, making them unreliable for model training. For other features like PM2.5, temperature, and relative humidity, we chose to retain and impute missing values using the median, which is a robust method for handling squid distributions. Once imputation was complete, we removed the outliers, particularly from PM2.5 values, to ensure our model wasn't misled by extreme anomalies. After cleaning, we transformed the PM2.5 values into three categorical labels according to the Air Quality Index standard. Values which are less than equal 50 were labeled as good, values between 51 and 100 as moderate, and values which are greater than 100 as unhealthy. This classification converted our problem into a multi-class classification task, which is more suitable for public interpretability and health-based analysis. To better understand relationships between features, we used correlationship heat maps. This analysis revealed a moderate negative correlation of minus 0.3 between PM2.5 and temperature, including that air pollution tends to reduce when temperature increases. Other variables showed weak linear relationships as seen by near zero correlation values and lighter heat map colors. One major challenge we encountered was class imbalance. The distribution of labels showed a strong skew. Most samples belong to the good class, while the unhealthy category and significantly fewer instances. This imbalance required us to carefully design our models and consider class weights during training to avoid biased predictions. We also visualized PM2.5 trends over time, which showed clear seasonal patterns and recurring peaks, particularly in the early and the later parts of each year. This confirmed that PM2.5 levels are heavily influenced by seasonal weather patterns and possibly specific human activities like traffic or industrial emissions. The project demonstrated that with effective data processing, particularly in handling missing values, outlier removal, and class imbalance, machine learning can be a powerful tool in predicting and monitoring air quality. That's all from me. Now I am passing the speech to my next speaker. Thank you.
Thank you for giving me the floor. Now I'm going to discuss about some of the models that are used in this project. The first model is the random classifier. We used random forest with 100 decision trees and depth of 20. It helped us to achieve 75.68% testing accuracy. It excelled in classifying good air, especially in the class 0, where F1 score is 0.82 and classes 1 and 2 had slightly lower F1 scores where it was 0.71 and 0.70. Its approach minimized overfitting and making it the most robust choice. Now I'm moving to the second model, which is the decision tree classifier. The decision tree classifier uses entropy-based splitting and a deeper structure with, with depth of 30. So it achieved 71.29% accuracy. While it performed well for class 0, it struggled with minority classes for class 1 and class 2. And the reason is the overfitting. And evident from the gap between train test results, regularization helped but couldn't match random forest stability. Now I'm moving on to the third model, which is the k nearest neighbors, also known as the KNN. It is a kind of distance based approach where we used Manhattan distance with five neighbors and matched decision trees accuracy with 71.01%. But it showed high recall for class 0, which is 0.80. However, imbalanced classes hurt its performance for moderate, or unhealthy categories. Its non parametric nature made it simple but less adaptable to complex patterns. Now I'm going to the last, which will I'm going to discuss is the Adabust classifier. So Adabust classifier is the weakest performer according to our project, and is we used 300 weak learners and had the lowest accuracy, which is kind of 63.26%. Despite iterative error correction, it failed to handle dataset complexity, and particularly for minority classes its high mean absolute error confirmed its limitation for this task. Rest of the models will be discussed by our next presenter, Tanvir Ahmed Shah.
Thank you, Najib, for giving me the floor. Assalamu alaikum, sir. I'm Tanvir Ahmed Shah, and today I will be focusing on four machine learning models used in our air quality prediction research for Bangladesh. Those models are XBoost, XGBoost, LightGBM, CatBoost, and neural networks. So XGBoost classifiers or extreme gradient boosting was our second best performing model with 74.11% of accuracy. The key implementation of this model are configured with 300 estimators, maximum depth of 8, and a learning rate of zero point 0.1. The performance metrics of this model were mean absolute error of 0.289 and the mean square error of 0.349. XGBoost particularly excelled with our imbalanced dataset delivering meaningful feature importance. This aligns with findings from other research such as the Azamgar study where XGBoost demonstrated outstanding R-squared values and computational efficiency. The model works by building multiple decision trees sequentially with each new tree correcting errors made by previous trees. This approach makes it particularly effective for environmental data with complex relationships between variables like temperature, humidity, and PM 2.5 levels. Our second classifier is the light GBM classifier. Light GBM came third in our evaluation with 71.68 percentage accuracy. The key implementation of this model were 300 estimators, learning rate of 0.05, and a maximum depth of 8. The performance matrices of these classifiers were mean absolute error of 0.318, mean squared error of 0.387. GBM's distinguishing feature is its self-leaf-wise tree growth approach as opposed to level-wise growth in traditional algorithms. It showed particularly high recall of 0.81 for class 0 good air quality, though it was less impressive for classes 1 and 2. The leaf-wise growth strategy allows light GBM to focus on the most promising branches, resulting in deeper trees with fewer splits. However, this approach proved challenging with our imbalanced dataset, potentially explaining its lower performance with moderate and unhealthy air quality classification. Our next model is the CatBoost classifier. The CatBoost classifier achieved of 70.59% in our testing. The key implementation of these classifiers were 300 iterations, learning rate of 0.05, and a maximum depth of 8. The performance metrics of this model were mean absolute error of 0.329 and a mean squared error of 0.40. CatBoost is specially designed to handle categorical features effectively using an ordered boosting technique to prevent target leakage. Despite its reliance against overfitting, its overall performance trailed behind XGBoost, and Random Forest. One potential reason for the lower performance could be that our hyperparameters weren't optimally tuned for this specific algorithm. CatBoost typically requires different optimization strategies compared to other gradient boosting frameworks. Our last and final model is the neural network. Our neural network model achieved an accuracy of 71.7%, comparable to light GBM. The key implementation of this model were sequential model with four dense layers, ReLU activation function, 10% dropout of regularization, batch normalization, initial learning rate of 0.0005, categorical cross entropy loss function, and softmax activation in the output layer. The performance metrics of this model were mean absolute error of 0.3168, mean squared error of 0.3858. The model was trained for 46 epochs, showing a clear downward trend in both training and validation loss curves. These curves stabilize after approximately 30 epochs, indicating proper convergence without overfitting. Interestingly, our tree-based model outperformed the neutral network approach, suggesting that tree-based methods may be better at capturing the complex interactions between air quality features in our data. So if I give you a comparative analysis, when comparing F1 scores across models, we can see that XBoost performed well on classes 0 with 81% and classes 1 with 69%. Neural network and light GBM achieved similar F1 scores with XGBoost. Light GPM had better recall for class 2 with 65% versus 64%. CAT Boost struggled with classes 1 and 2. F1 scores around 0.66 and 0.66. The yearly comparisons of actual versus predicted AQI values showed improvement in our model's accuracy over time, with larger gaps in 2013 and 2014 that decreased in subsequent years. In conclusion, we can say that while random forest remains our best performer at 75.68% accuracy, these four models offer valuable insight into ER prediction in Bangladesh. The performance could potentially be improved by addressing class imbalance issues, further hyperparameter tuning, incorporating additional meteorological and pollution source data, developing real-time prediction system. Also, our model, also as we have to deal with a huge amount of null data, our accuracy was limited to 70 to 80 percentage most of the time. The models we have described today can serve as effective tools for ongoing air quality monitoring, public health intervention, and policy decision to migrate the negative effects of air pollution in Bangladesh. Thank you for your attention. Uh, that's all for our project. Thank you very much.